It's full. What is this room? Are you not cold? Why am I cold in here? Am I the only one cold? Hopefully, I get to go to bed. Oh, yeah, I guess I will be here. Okay, so today we're going to do second order ODEs, and they sound really complicated, but Brandon's going to show you that it's actually not as scary as you think it'll be, right? Okay. And everyone's gotten these coupled first order ODEs. So they were able to do the homework from last week, and they got something that was really reasonable. They saw a butterfly, and they're like, whoa, sick, right? Okay. Any questions before we start? I did note that all of my notes that I put into your homeworks don't show up for you. So I'm going to put them into a section that's called grade. It's not really a grade. It'll just be my comments. I'm just going to copy and paste it and place those all there. It just won't look as pretty because it's like a tiny box like this. So maybe, I don't know, click it and make it larger. Okay, any thoughts, comments, questions before we start? All right. Brandon, take it away. In this section, and they're actually not that different in first order. Okay, let's pause for 1 second. What is a second order differential equation? Anyone but Brandon? I just had to start shouting. That would be warmer. Second order, what does it mean? What is second about it? Yeah, that's true. Okay, so it's the second derivative. And then ordinary means what's that? What does ordinary mean? Basic. That is a definition, but not in this context. All right, last one. What does equation mean? Has an equal sign. Good. Needs an equal sign. What does differential mean? There's derivatives. Good. Okay. What does O in the ordinary mean? What does that mean? No partials. What does that mean? An ordinary differential equation is one in which the function only has one variable, or the variable that you're taking the differential with respect to, right? So everything can depend on time, right? That's perfectly fine. You could have something like this. There's only one dependent variable, and that's time all the way through. Does that make sense? As opposed to a partial, which has a completely different symbol, right? And so what makes it second order? It's written on the board. Good. So let's write this whole thing out. Is that right? Raise your hand if it's right. What? Yeah, so I'm actually going to use the 2 notation. But yeah. Cool. All right, go ahead, Brandon. Moving down. Then you can see the expression on the next line. So the trick there is to actually replace the dx of dt with 1. And in terms of the equation, you know, dy of dt x of f of x of y. So essentially reducing the second order to the first order, and we can utilize the same techniques for so moving down. We can apply this to higher orders. So in the case of higher orders, we can do the same thing, but remember the first part must be a derivative of the nth order. In this case, it's the third. So we have the x of dt with y dt is v. The whole function is going to be dz of dt. The function. You can also generalize some further. We can just say that the dependent variables are vectors. We exercise the derivative, second derivative of vector r with respect to t. You can also apply the method in this vector. Okay, so let's pause for a second. Does that process make sense? What are we doing here? d dt quantity squared of a function. Maybe let's make it a little simpler. Let's make it with respect to x is some function of x and t. Is that easy to solve? Yes, it is. Because you all done it. You just didn't know you were doing it. This is simply 2 coupled differential equations. So I used x because that should have a physical interpretation for you. What is the second derivative of x if we're talking about t being time and x being position? What's that? There's a physical interpretation. So imagine that x changes with time. The second derivative of the position with time is the acceleration. Okay. So in fact, you can say something like this, right? You ever said this before? What's the v there mean? The velocity. And what does this mean? What's that? What does the whole thing mean? Sure, on the right-hand side, what does this mean? The what? The rate of change of the velocity with respect to time is by definition the acceleration. So in fact, we know this quite well. So you can either say this statement up here, which is that the acceleration is something, or you can link it. And you can say, well, really, I'm solving 2 equations that are ordinary differential equations, first order, right? And you just did that twice on Monday. So now you're experts at it, right? Wobbly, but we're going to practice more. Okay. Go ahead, Brennan. So let's pause for 1 second here. What does this left-hand side mean? This here? Right, right. So this is essentially saying something the angle's changing as a function of time. And this is the description due to the angle, right? Okay. So if I looked at this as Newton's second law, which one is the force and which one is MA? Exactly right. So here's M. Here's what's essentially A, right? Because this is the angular acceleration, and it's due to gravity. So if it's hanging straight down, there is no acceleration due to gravity. And if I lift it up, there's acceleration due to gravity, right? So the acceleration on the left-hand side is due to gravity. Good. We already said we understood acceleration, right? Okay, so we're just doing now angular versions of the same thing. Go ahead, Brandon. Yeah. Does that look similar to folks? They're so used to it, they're falling asleep now? Okay. And the rest of the problem is left to you. Ooh, we love that part of a text, right? This is less as an exercise to the reader. Okay. So I think we do it, right? I think that's the agenda for today. Let's see. Is there more that you wanted to say, Brandon? Hair exercise. Yeah, 8.4. Let's fucking go, boys. All right. We excited? I don't think hello, let's hear it again. Are we excited? Yeah. All right, that's fine. Let's get into our groups that we had on Monday because we crushed that homework and everyone left like an hour early. So we're gonna do the same thing today, and we're just gonna fucking go right through this material. It is not hard. It's just tricky. So what I mean by that is we are not going to take huge cognitive leaps here, right? We're not doing something brand new, but we're taking a technique that we've used before and we're applying it. And so when I say being tricky, that means being aware of the mistakes that we might make, which is either copying and pasting the wrong stuff, not using the right letters. Let's say, I mean, how many times did we run into people who had A like 4 or 5 different times, right? I think almost everyone did that. So we just want to be a little cognizant of, we're going to borrow the code that we used from Monday because we knew that it worked. And then we know that we have to make certain changes, right? But we want to be cognizant of those changes before we make them so that we don't accidentally rename stuff or get the wrong answer or anything like that. That make sense? Okay. We're gonna make we're gonna take 845 and 846 and turn it into a fourth order Runge-Kutta for a pendulum with those variables. And then this asks you to create an animation. We are not going to do that. Anytime that it says do an animation, just don't. Okay, you can just like take a frame every 10 seconds and plot where it is every 10 seconds. I'm perfectly okay with that too. Okay. And I can show you how you plot every 10 seconds. Okay. That was really quick. We got through that very fast. So I'm expecting there's no questions, not a single question from anyone. Not yet. Okay, that's the right energy. All right, so let me pause this then.